In this demo, we're going to take a look at dynamic memory allocation. And in order to do so, what we've done is created two pointers, one called pint, which is a pointer to int, and one called pdouble, which is a pointer to of type double. Rather than initializing pint and pdouble with the address of a variable, which is something we've done in the previous demos, we see the use of the keyword new and the data type on the right hand side of the assignment statement, and in this case the new double down here. So what this is telling us is that we are asking the operating system to give us a memory address to store a variable which will be of type int, and in this case to store a variable which will be of type double. Now that's important to keep in mind, because as we've said before in our discussions around pointers, you have to ensure that the pointer you're using is of the proper data type for the value that you intend to store into it. And again, the reason it's important is because the operating system needs to know how much memory to allocate for that value that will be stored. And if you attempt to store a double value in the memory address that's been allocated to pint, it will be too large. A double is essentially 8 bytes, the int is 4 bytes, so we will actually go beyond the memory address that has been allocated by the operating system. Now, in modern operating systems and compilers, that assignment wouldn't be allowed, so there would be an exception or an error generated to kind of tell you that. But on older systems, that could have been a source of problems, bugs in the code, because you were storing a value that was too large for the memory that was allocated. So once we have assigned a memory address dynamically from the operating system to these two pointers, we will then use the dereference operator and we will assign values to those. So in this case, we'll assign 3 to our memory location that's pointed to by pint, and then we will assign 5.0 to the memory that is allocated to pdouble. Once we've done that assignment, we'll then print out the value that is stored at each one of those memory locations, and we'll use the dereference operator to get access to the variables. And we'll also print out, just for our own purposes, the address of those variables as well. And then what we're going to do is take a look at how C++ deals with the size of address pointers versus the size of the values that are stored in them. And then finally, we're going to release those pointers down here at the bottom. So let's start this code with a Control F5, and I will just drag this off to the side so we can once again scroll and take a look at the code that gets executed and what the output looks like. So we've declared our pointer variables up here. The operating system has returned dynamic memory addresses for these two variables. We have assigned values into those two memory locations, and then we start our output statements. So in the first one, we're saying that the value stored at pint is, and again using indirection we get the value. Then we output the memory address of that variable. So in this case, we can see the value stored at pint is 3, which is what we assigned, and the memory address starts at 9B0210. So this is a hexadecimal memory address. Our next line executed was basically the value stored at pdouble, which was 5. You'll notice a difference because we stored 5.0 and it's only outputting 5, so it's basically dropped off the fractional part of that value, and that's perfectly fine. I haven't used format specifiers to indicate how I wanted this to display. Just know that we're actually storing that value in that memory location. And then we get the memory address for pdouble, which is, in this case, is 9B2228. And again, these are dynamically assigned from the operating system. We have no say as to what those memory addresses will be. Then we output our size of statements down here. So in the first one, we're dealing with, again, our pint, so that the size of pint, and pint is a pointer which stores a memory address, so the size of that is 4 bytes. So that basically means that the pointer is of size 4 bytes in order to store that memory address. But the size of the value stored in pint is also 4. Now that just simply means that we are storing an integer type in pint, or in that memory location, and an int type in C++ on this particular computer is 4 bytes in size. Now if we look at the double, the size of p double is still only 4 bytes, but yet the size of the value stored there is 8. So why is there a discrepancy between these two? Well, again, for the memory architecture in this computer, a memory address fits within 4 bytes of space. So this is why the size of our pointer is 4 bytes, regardless of the data value stored in it. But the value stored in p double is a double, which is twice the size of an int, so therefore it's actually being stored as 8 bytes in the computer. What that essentially means, you can perform a little bit of memory address arithmetic, or pointer arithmetic if you want to, in taking a look at saying if the size of my pointer int is 4 bytes, the value should be 4 bytes in size that's stored in that memory location, then essentially the values would be stored in 9B0210, 211, 212, and 213. That's my 4 bytes of memory address space. Likewise, if we did the binary math or hexadecimal math, if you will, on this memory address, we would find 8 bytes of that added, 8 bytes added to 9B2228 would give us the ending address of what p double would be, and so the value wouldn't go beyond that. So once we've executed all of these statements, it's important for us to actually release the memory back to the operating system so that other applications can make use of it. And that's what the 2 delete statements are doing down here. We're not outputting anything specific saying that the memory has been deleted, because once we delete the memory address or the memory that's associated with these pointers, those pointers go out of scope and they're no longer available, so we can't really do anything with them. If we attempted any line of code that acted on pint or p double after we've done the deletion, we would generate errors in the code. So it's important to always ensure that every time you have called the new keyword, that at some point in your code you're calling a delete keyword to also release those memory resources. That'll change a little bit when we start talking more about objects in the next module, when we start looking at creating new objects from class files, because we deal with constructors in a class file. When we create or instantiate an object of that type of class, we will deal with something called a destructor in that class, which is similar to this delete keyword. Delete is used for these particular types of pointers because we're pointing to intrinsic or built-in data types. So that's a demo on dynamic memory allocation. And again, this is using just intrinsic or simple data types. You'll revisit dynamic memory allocation using the new keyword when we delve deeper into some more of the class files and working with objects that are class files rather than intrinsic data types in the next module.